we are here, and what we will see today is how to do a filter now in frequency. So we saw it. So the main theme of the last lecture and this one is filtering. So you have, let's say, you have an image. I go through a filter, and then you produce a new image, J. And then we saw, and this is just a convolution. So what we saw in the previous lecture was how to compute this convolution in real space. And we said, okay, so in real space, this is the sum over all pixels of I of n, and then h r. So this is the convolution, and then we call this the moving window. We call this the moving window because the kernel is moving, and for every position of the kernel, we multiply and then add all the values there. And then we also said, okay, but these you can also compute in this way. So you can compute like you. So you have to shift the image to all the locations of where the kernel is, multiply by the coefficient of the kernel there, and then you add. And we call this one, we call it shift multiply. Okay, so what we will see today is that you can also do that through a Fourier transform. So you can say this is the inverse Fourier transform, or the Fourier transform of your image times the Fourier transform of the kernel. So that is what we will see today, and this will be through the Fourier transform. So you can compute the convolution in 3 different ways. So 2 of them are in real space. The third one, that is today, it is in Fourier space. And this is a property that you already know, right? Okay, so let's put it. So let's say that we have 2 signals. So x convolved with h. You do the Fourier transform. This is x, the Fourier transform of x times the Fourier transform of h. And because of the duality, you have the multiplication of 2 signals. Then if you do the Fourier transform, you have a convolution of the 2. This operation is a convolution. This one is masking. So masking means you have an image. You multiply by another image that is typically like 0, 1. So it is, let's say that I want to keep this region, only that region. So here it is 1, and outside it is 0. So I'm masking the full image within this region. And then the Fourier transform of the masked image, so the one that is multiplied, is the convolution of the Fourier transform of the original image convolved with the Fourier transform of the kernel, the mask. Clear to hear? Okay, good. So then, let's see how to do these filters. So let's go here. So these are the 2 properties that I mentioned. So you have the Fourier transform of a convolution. It is the product of the two Fourier transforms. If you have the Fourier transform of a product, it is the convolution of the 2 Fourier transforms. So we will do it this way. So we have an image. We have the Fourier transform of that image. You have a kernel that you want to convolve this one with this kernel. And then you do the Fourier transform of this. you multiply point by point the two Fourier transforms, and then you do the inverse Fourier transform. So this is another way of doing the convolution. And this one, what happens at the borders? And here I don't think they are discussing that. So what happens at the borders? So the Fourier transform, you may remember from the lecture on the Fourier transform. Let's say that you have an image here. So when you do the Fourier transform, you have something that is something like that in 2 dimensions. So it is this representation. Okay? So it is this function here. But that function there is made of deltas. So it is made deltas. Because those are the ones that you can keep in the completed. So that means that you are assuming that the image is periodic. When you have infinitely many repetitions of this image everywhere, so, and you're repeating from minus infinity to infinity. And now we do a convolution. So now we do a convolution with this kernel, let's say. So we know what we have to do is to move this kernel all over the place and compute these stamps that we said before. What happens at the borders? So at the borders, you are convolving a part coming from this image and another part coming from the nearby copy. Okay, so you're assuming that in the borders, you have this periodic repetition of the image, so that this assumption that we had to do when we computing not assumption, but this decision that we had to do when we computed the convolutions in real space that were here. So the convolutions in real space, they were these ones. So outside the image, we were assuming, okay, it is 0, or there are some other assumptions. So one of the assumptions is this one. So it is periodic, and it is the one that the Fourier transform convolution is doing. Okay, good. So yeah, this is MATLAB code to do that. This we already know that the Fourier transform, or if you compute the Fourier transform of an image, the origin is there. So all these it goes from low frequency to high frequency and then low frequency again. And you can do the FFT shift that moves the origin to the middle of the image so that all the low frequencies are here. So the ones that we are showing here are the ones in which the origin is in the middle of the image. Okay, so that is the low frequency. Very good. Then, yeah, all this is that. So let's do a low pass filter. So if we do a low pass filter, so we can do low pass filters in many ways. So what is a low pass filter? So low pass filter is one. I will do it in 1 dimension because it is what I control easily. So one in which the Fourier transform of your filter. So this was called the ideal low pass. Ideal low pass filter. And you remember that if you do the inverse Fourier transform, the response is a single. Okay, so this is a space, and this will be H of a space. Okay, so it is a sink. So this is the ideal one. What about non-ideal ones? So you can, for instance, be very flat and then go smoothly to 0. This could all speed. And the inverse Fourier transform, it will be some kind of similar to this one. So it will be similar, but it will decay faster. That is the difference. So it will go to 0 faster than the sink. Then what else? We can do something that is something like this, for instance. This is also a low pass filter. So anything that attenuates at high frequencies is a low pass filter. So you can have an ideal, you can have an ideal with a smooth borders, you can have something that decays with frequency. So this is what it is explained here. So what is a low pass filter in real space? It is averaging, and in frequency space, it is something that high frequencies are attenuated or they go to zero. And this is one of them. So 1 over omega is one of these low pass filters, right? Because 1 over omega, let's do it with a different color. 1 over omega is like this. So high frequencies are attenuated. Okay, so what else? Then this is the same. We have the same. So let's apply ideal low pass filters. So the ideal low pass filter look like this. So it is a 1 everywhere in the low frequency, and then they go to 0 very abruptly. So it is like this one that we said that ideal. I didn't put numbers, but this one is 1. Okay, so the height is 1. This is called the cutoff frequency. So the frequency at which it goes to 0, it is called the cutoff frequency. So this circle here is like the 2D version of this step function that I draw in one dimension. Now, what is in Fourier in real space? So if you do the inverse Fourier transform, it looks like this. That should look like a kind of ceiling. And here we have it for one profile, so for one line. So in one line, in Fourier space, it looks like a step function, and in real space, it looks like a ceiling. Okay? So we are convolving with that. So convolving with this, multiplying with that. What if I make my Fourier transform, my low pass filter even narrower? So if it is narrower, because of this uncertainty principle that we said, something that is very compact in one space has to be wider in the other space. So now it is more compact in frequency space and it is wider in real space. So now the sink is bigger. So that means that we are averaging more. So all the pixels within this region will influence a given pixel. We can compare it with this one, where this region is smaller. Very good. So then let's take this image. This is its power spectrum. This is the phase. Now we multiply by, this will be the low pass filter in Fourier space. Now we multiply the Fourier spectrum. So it is this one multiplied by this. So it is this one. This is the power spectrum of the filter image. So everything here is 0 except this region. And then you do the inverse Fourier transform. And this is what you get. So what you have is a blurred version of the original image. How much it is blurred depends on how large this filter is. Okay. Very good. Then, yeah, this is the same image. Like so that you can compare. Okay, good. Now let's do an ideal high pass filter. So how do we do ideal high pass filter? So the ideal high pass filter would be this one. So let's say high pass filter omega, and omega goes to 1, then it has a cutoff frequency, and it is this one. But this I can write this way. So what if I do 1? Okay, so this is 1 minus this one, but it's a low pass filter. It's a low pass filter. Do you agree with that? So I can compute the high pass filter with this Fourier space. So it is a constant minus a low pass filter. And now I'll give you the inverse Fourier transform. Transform to the minus one. Okay, so the impulse response, the high pass filter, now is in real space, will be the inverse Fourier transform of the, let's use the same colors. So the inverse Fourier transform of this is delta y. And now minus the impulse response of the low pass filter. So it will be a delta minus an inverted C. See if that is true. So this is the high pass filter, and this is the impulse response of that. And the impulse response looks like a delta minus the sink. Okay. So we are convolving with this. So let's apply it. So we have the original image, the original power spectrum, the low pass, the high pass filter. Then we multiply the power spectrum by the Fourier transform by the transform of the Fourier of the high pass filter, and then we do the inverse Fourier transform, and this is how it looks like. So we have lost the low frequency details. So all we see are the borders. Any question? Okay, so bandpass filters. So a bandpass filter is this kind of construct. So we leave some regions in the frequency space that can pass. So let's say the two cutoff frequencies, so one that is smaller, another one that is larger, will be rho 1 and rho 2. So we can construct this filter as a low pass filter with rho 1 minus a low pass filter with rho 2. So now we understand that Fourier, the impulse response of this one will be the sink associated to this minus the sink associated to this one. Very good. So now let's do the two low pass filters. So one is bigger than the other. So the one that is bigger is rho 1. So we let more frequencies pass. So it will blur the image less than the second filter. So the first filter blurs the image, but the second filter blurs even more. And now we subtract the two. Because if we say, let's do it in here. So we have constructed our bandpass filter, at a given frequency. We say it is H1, that is low pass, call it 1, minus H2. So let's convolve with this one. So let's convolve with that. So we have an image convolved with the impulse response of this. That will be image convolved with the impulse response. First one minus the second. But this is the convolution with the first. So this is the convolution with the first minus the convolution with the second. That means you do two low pass filters. You do two low pass filters and then you subtract the two. And this is the result. And you can see that in a Fourier space. So this is the power spectrum of the filter. And what if I make my low pass filter even narrower? So now I'm letting fewer frequencies to pass. In the limit, what happens in the limit? So in the limit, you remember what we said about having a Fourier coefficient. So when we said, okay, I have a frequency space, this is omega, space, and then I have this component. So you do the inverse Fourier transform, this would be kind of wave propagating in this direction. So propagating in this direction. I'm not too good at drawing, but okay, so let's say this is black, this is white, this is black, this is white, and this is the real space. Do you remember this kind of drawings we were doing with the Fourier transform? So now, if we have a very narrow filter, so what we have is the same, but now with all the waves of a given frequency, but that they are propagating in the different direction. Well, this is that. So the narrower you make it, the more similar it will be to just a single frequency, but now in all directions. And then what is the component of a given frequency of a particular image in all directions, but just one frequency. So the narrower you make it will be just one frequency. Any question? Okay, so then we have this uncertainty relationship. The uncertainty relationship says if something is relatively small in in real space, in frequency space it will be wide. If it is wide in real space, then in frequency space it will be narrow. And there are some lower bound of how the support of this and this relate, but we don't care about that specific bound. And we have this kind of reasoning that, for instance, in this direction, it is very narrow. It's extremely narrow. This is just a point. So in this direction, it has to be very wide. It is a constant. What about in this direction? So in this direction, it is a couple of deltas. So very compactly supported. So here it will be very wide, but in a different way to this one. So in this direction, it is a constant. In this direction, it is a sign. What if I make in this direction, I make it very wide? So if I make it very wide in this direction, in the real space, it will be very compact. So it will be zero everywhere, just a line, and then zero again. So we have this kind of reasoning. And that is the reason why these kind of ideal low pass filters that are very compact in one space, they go very far away in real space, and they go like oscillating. So when I apply this kind of low pass filters, for instance, to an edge, then what I have is the convolution with the sink. The convolution with the sink causes these oscillations, and these oscillations are something unnatural. So let's look for a different low pass filter such that we don't have these oscillations. And it turns out that from the point of view of the uncertainty relationship. So in this uncertainty relation, if something is wide, it's narrow here, it is wide there. So we can think of, and you have the support of this function and the support of this one. And we said the product of the two supports is larger than something. So we can think which is the function that gets closer to that lower bound. So that it is as compact as possible in one space and as compact as possible in the other space. And the function that fulfills that is the Gaussian. So the Gaussian, that is this is the one-dimensional Gaussian. So the Gaussian is the function that maximizes the compactness of the support in both spaces at the same time. So it gets closer to that lower bound. And this is the two-dimensional Gaussian. So now it is a kind of band. So it is the same kind of shape that we had here, but now in 2 dimensions. And you can have 3 dimensions, 4 dimensions. And in general, the formula is this one. There is an even more general formula. So let's say that there is the original or the more general Gaussian can be kind of ellipsoid. This is the formula for kind of symmetric Gaussian. But so it looks like the product, it is actually the product of Gaussians, one in X, one in Y. So one for the rows, one for the columns. So if you take this one that is in 1 dimension and you apply it for the rows and you apply it for the columns. Then you have the symmetric Gaussian. Very good. So now when you compose with the Gaussian, now you don't have those oscillations anymore. And also it is interesting, the Fourier transform of a Gaussian, yeah, it's here. So you have a Gaussian in the Fourier space. The inverse Fourier transform is also a Gaussian. So the Fourier transform of a Gaussian is another Gaussian. And it is the one, so now in a Gaussian we don't have oscillations. So because we don't have oscillations, now we have a smooth transition from one side of the step to the other one. And you can compare with the ideal low pass filter. So you see here, you see the oscillations in the Gaussian filter one, you don't see that. Very good, and now we have Gaussian low pass filters. So you multiply by a Gaussian in Fourier space, or you convolve with another Gaussian in real space. And if it is wider, for instance, in real space, in Fourier space, then in real space it will be narrower, but they will always be Gaussians. Okay, so in frequency it is wider, and in real space we are convolving with a narrower Gaussian. So let's see some examples. So let's say we have that image. This is the original power spectrum. This is the low pass filter. Now you multiply the power spectrum or the Fourier transform by the low pass filter, and you invert, and then you have this blurred image, but blurred with the Gaussian, and you can compare to the ideal low pass filter that we have covered. Let's go to the ideal low pass. Now in the ideal low pass, we see the oscillations. Okay, and in the Gaussian low pass, there are no oscillations. Very good. Now Gaussian high pass. So we do the same trick. So it will be 1 minus the Gaussian low pass filter. So it is 1, that is a constant, minus the Gaussian low pass filter. So it is the 1. And the impulse response will be delta minus the impulse response of the Gaussian. So it is this one. And yeah, when you multiply the two, this is what you get. So this is the filtered one. And now we have the filtered image that is a filtered high pass, but now without oscillations. You can make it bigger. So now we have a very big, so very slowly growing high pass filter. So that means that even fewer frequencies here, low frequency from the original signal will pass. And now what we have are finer edges. So we can compare this one with this. So because here you are letting pass many frequencies, you have most of the details. It's true that you have lost the very low frequencies, but here you are even losing even more. So the more you lose, the more you will go to just the edges.
Go something like an ideal high pass or low pass filter, but with the maximum main lobe width.
Yeah, so this is if I understand the question, this is a high pass filter with a bigger lobe.
Yes, like when we studied last year about the filters, like we knew that whenever we compare it to the main lobe, the secondary lobes would get higher. Like in the
Okay. Yeah, but here there are no lobes. Because
what I'm saying
it is a Gaussian.
What's the difference between maximizing the main lobe of an ideal filter or applying a Gaussian? Is it the same?
Here there is no second lobe, so it is not the same. The sense there is a main lobe, but there is nothing else. So it is not, you cannot maximize the first with respect to the second or so on, that you can do in some other kinds of filters. You could also do the same idea in 2 dimensions, but not with Gaussians. Relation is this thing. So in the ideal low pass, here, the impulse response goes up and below 0. Okay, so it goes below 0 and then above 0, below 0, above 0. So,
But why is that ideal? Like, it wouldn't be normal.
so ideal low pass filter is 1 up to a frequency and then 0. That is the ideal low pass filter. And the impulse response of that oscillates. Okay, because you know that the impulse response is a sync. Sync in 1 dimension. In 2 dimensions, it is something called jink, but kind of something that oscillates. Okay.
And in the Gaussian, it happens also the same.
No, in the Gaussian, the Fourier transform of the Gaussian is another Gaussian, so there are no oscillations.
So that's better.
Okay, so yeah, we were here. So now Gaussian high pass, we were seeing this one. Gaussian band pass, or Gaussian band pass is the subtraction of 2 low pass filters. So it is the same. And the concept is the same. So you convolve with a large Gaussian. So a large Gaussian in frequency space will be narrower in real space, so you don't lose so many details. Here you are losing many more details because in Fourier space you are narrower. Okay, so you're convolving with something bigger in real space, and then you are blurring it even more than here. And then you subtract the 2 and you have kind of bypass. And this is the filter power spectrum. And these are this is the impulse response. So the impulse response is a Gaussian minus another Gaussian. And then it is this one spatial domain. You have kind of delta with some undershooting. And then, so it's the multiplication of the 2 with different factors, sigma factors. And then we can compare ideal with Gaussian filters. So the ideal low pass filter is this one that has oscillations. And this is the ideal high pass filter. And then we can compare to the Gaussian low pass filter. So if I move from one to the other, look at that one, you see the oscillations. And you see the oscillations caused by the ideal low pass filter. And the same here for the high pass. In the high pass, in the high pass, here you see the edge, but here you see the edges and the oscillations. So ideal filters, they are good for mathematics, but they are not good for visualization. And bandpass, ideal, Gaussian, then you can compare the two. And then there is some little thoughts about what happens with the power spectrum. So this is the original image, this is the power spectrum. The power spectrum, we know it is the module of the Fourier transform square, and then the phase spectrum. And when you do a low pass filter with a Gaussian, then this is the power spectrum of the output, and it makes sense because we have multiplied by Gaussian and then it goes to zero. But what about the phase? The phase doesn't seem to change. So let's look at the phase originally. So this was the original phase, and now the final phase. It doesn't change. Why doesn't it change? Let's look at the mathematics again. Okay, so let's, we were saying, okay, so we are here. So we are multiplying the Fourier transform of the image with the Fourier transform of the filter. How is the filter? So the filter is a Gaussian. Frequency is H, and is a Gaussian. Okay, so let's do that multiplication. So let's do the multiplication. So we have a signal times the kernel. Okay, so this will be the signal I can express as the amplitude of the signal times the phase of the signal, so x, times, and the same for this one, and the phase of h. Okay? And now it is a Gaussian. So if it is a Gaussian, that means that this is a real number. If it is a real number, the phase is always zero, and this is one. So this is equal to the amplitude, and then let's put it this way. Amplitude, and then the phase x. So that means that I'm modifying the amplitude, but I'm not modifying the phases. And because this one never goes to zero. So it is not like the ideal low pass filter. The ideal low pass filter at some point it is zero. But this one never goes to zero. So that means that I'm never multiplying by zero. So the phase survives the filter always. Okay, so in this one is attenuated. We don't see the power there, but the power is still there. It is multiplied by a very small number, but at the phase doesn't change. It is the same phase. And do you remember? Most of the visual information is in the phase. So Gaussian filters, in that sense, they are very good because they don't modify the phase. They only touch the amplitude. Yeah. What else can we do with this? Okay, so let's say that I do the following. Okay, so let's go down again. So I do the following. So this is the power spectrum of I. This is the power spectrum of I. And we said most of the images, they decay somehow as frequency squared. You remember that? We said most natural images, they decay. Okay, what if I convolve with something that is like this? So my kernel, let's my kernel. So my kernel frequency starts at 1, and now it is kind of Gaussian, but in the opposite direction. So it is it's kind of. So how can I construct that? So it will be, so my Fourier transform of the boosting, it's called boosting, will be 1 plus a high pass filter, Gaussian high pass filter. So Gaussian. So what if I do that? So now the frequency will be this one after multiplication will be I'm multiplying by 1 and then by something else that is a little bit bigger and bigger and bigger. So what I'm doing is giving more amplitude to the high frequencies. So I'm giving more energy to the details. So I have the original image, okay, and now I multiply by that, and then what I have is sharper edges. So the details have more energy. And I would say you see better this image than this one, right? So you see many more details there. And now you can connect it to our visual system. We said that when we started the visual system, we said we only see the edges. Now the edges have more energy because we have multiplied by something that gives more energy to the high frequencies. So the edges have more energy, and that is why we see better this kind of boosted images than the original ones. Any question? Very good. So then let's stop here.